Okay. And there we go. All right. So last time we started looking at the solutions of the transfer equation. We spent some time on the uniform slab approximation. So that's the most important aspect. This you have to remember by heart. This expression for the emergent intensity from a uniform slab is something you should know by heart, okay, in any field of astronomy. We will now look at various approximations to the transfer equation in the limit of very optically thick media. Because this solution to the uniform slab is only valid, I mean, this solution here, I've said you should remember by heart, this is only valid when you have a constant source function, so constant temperature, no scattering. And yes, so constant source function means that you cannot apply it to lines either, because the source function for the lines depend on the excitations of the atoms and molecules. Okay, so if we want to we can extend the transfer equation and find analytical solutions in simple limiting cases. The first observations we'll do is the first observation we'll do now is that in an optically thick medium we have a random walk. Okay, so if you look at this logo I have here on the upper right, this is a sketch of a star. Okay, so imagine you're inside a star and you have nuclear fusion going on in the core, which is very hot. You know, imagine that you have a photon being emitted inside the core. This photon will undertake a random walk, randomly to fly, randomly traveling to nearby spots in the star where it is absorbed again and re-emitted and absorbed and re-emitted, resulting in this random walk pattern until it finally reaches the photosphere, where the optical depth to its frequency is of order 1, and that's where the photon can just escape freely from the star. Okay, but what goes on inside the star is a random walk. Okay, and this process is applicable to any optically thick medium. So that can be a very different medium, not only a star. It can also be a protoplanetary disk. It can be the dusty torus around an AGN I've mentioned a couple of times before, and so on. There's several examples. Okay, so let me set up my tablet. Okay. Now I need my notebook. Right. So the idea is that the photon then will proceed with a random walk, and its net displacement is therefore the net displacement of the photon is the sum of individual steps, okay, of n steps. This is a vectorial sum, okay. So the dispersion in this displacement, if you calculate that's strange. Okay. So if we calculate sigma of r, typically we will calculate the variance of r. Okay, so the variance of r, and that would be like that. That is then the average of r minus its average squared. Okay. So I think you all know this, and since every single step is isotropic, it doesn't have any preferred direction. This average is simply 0. Okay, and so we need to average the norm of the net displacement. Okay, and so you replace this norm by the double sum. Okay. And then you reach the conclusion that if all steps are statistically independent, so I mean, the next step will not depend on the previous one in terms of the direction. Okay, these can be, I mean, if these two are statistically independent, then the average can be propagated inside the dot product. So what I mean is this is equal to the sum of the average of S and J when they're different, plus the sum of I and J with the Kronecker delta when they are the same. Okay, so it's I dot Sj. But this one is 0, of course, because each average is 0 on their own. I mean, and so we're left with simply the sum from 1 to n of S I squared. And we assume that all the steps are the same. Okay, so this is simply n times the length of each step. Okay, so that would be the variance, and this is squared. Okay, so this is how we reach the result that the dispersion of this on the displacement is the square root of n times L. Okay. Now, the probability of an absorption where the random walk is terminated for that photon is this epsilon. So that would be the probability of absorption. So what we're trying to express here is that you remember we have this absorption coefficient. Okay, so the absorption coefficient we define this way. So we have the transfer equation. So that's the absorption coefficient. Okay, alpha. And we know that for a constant absorption coefficient, then we have this exponentially decaying law. Okay, so we interpret alpha s as this would be like then the intensity at S. So minus alpha s is the survival probability. So if there is something I say which is not clear, please say so and I can repeat. We've looked at this a couple of times already, so I'm assuming that it's all clear for everyone. But if it's not, please say so. And so the idea here is that that would be the survival probability for the path length of linear dimension S. Okay. So alpha would be if alpha S is much less than 1, optically thin limit, then the survival probability is approximately 1 minus alpha S. Okay, so alpha S would be the absorption probability. Now I say absorption because this is the absorption coefficient, okay? But we know that there's two different absorption coefficients. There's the real absorption one, where the photon is absorbed and the energy of the photon goes into the absorber. And there's also scattering, where the photon is actually reflected and undergoes the random walk. In terms of line emission, we have that the distinction is not so simple, because we have the reflection of a photon follows absorption. Okay, but in terms of a continuous medium, we have the two different processes, so absorption and scattering. Okay, so the probability of a real absorption would be then in a single step, which is for a single step, then let me add another one. And so for a single step, so then S is of order L, the mean free path. Okay, and this ratio alpha A divided by alpha A plus alpha scattering is the probability of absorption. Okay, so so then, since all the steps are statistically independent, so for n steps, the probability of absorption then is for n steps, then the probability of absorption is simply n times epsilon, okay, because they're all statistically independent, okay. But of course, there's a limit, right? Because this eventually becomes larger than 1, and then it's not a probability anymore. If n goes to infinity, n times epsilon is eventually going to be larger than 1, okay? So we need to, this doesn't go on forever. And basically we say that, eventually this will go to 1, okay? So the maximum n is n 1 over epsilon, okay? So the number of steps before absorption is going to be 1 over epsilon. That's number of step before real absorption of a photon. Okay. So if we have an infinite medium and one where the photon will never reach the edge. I mean, for instance, if we have the interior of a star, which is a very big medium, and if the medium is arbitrarily large, then this random walk we started looking at. I mean, this this relationship here. Where did I put that one? Okay, so this relationship we derived, this one here, is not going to work. I mean, we cannot have infinite number of steps, right? I mean, the photon will scatter 1 over epsilon times before reaching a real absorption. It could even scatter less than that. It is a it is a stochastic process. It can be absorbed on the first step, okay, or it can survive a bit more than 1 over epsilon. But in general, on average, n is going to be 1 over epsilon, okay? So for in the case of an infinite medium, then we have that sigma of r is going to be square root of n, which is square root of 1 over epsilon. No. Let me see. Oh yeah, no, that's correct. Square root of n times L, okay? And that is 1 over epsilon times L. So I think I have a typo in my summary. There should be an L. Yeah, I mean, I think that I'm missing an L in the summary. I'll fix it right away, otherwise I'll forget. Okay, so now this is an L, and then this net displacement is called the thermalization length, means that this is the maximum displacement you can expect for a photon before it undergoes real absorption. Okay, so what happens after a real absorption? Well, the photon could be re-emitted. It could be re-emitted locally and undergo another scattering random walk. So what we're looking at here is a scattering random walk, which can end in a real absorption. Okay. Again, for a line photon, if you emit, if you have interactions through in bound systems, which are quantum systems, then the absorption, the random walk process is intrinsically an absorption process. I mean, you do not get scattered. The photon is absorbed by the target and then re-emitted with the same frequency. Okay, so that is the equivalent of scattering for a line. Okay. Now, if we go into this continuum description, then we have a scattering and an absorption part, and you can distinguish a random walk from absorption, which is right. So the photon will travel until it is absorbed in the first encounter because there's no scattering. Okay, so pure absorption. It is absorbed and then re-emitted. You could look at it as a random walk too, except that for a continuum process, the re-emission is not necessarily at the same frequency. In fact, we'll see that when you go to the continuum approximation, the re-emission occurs at the local conditions. The temperature could change. What I mean is, the example of a star is very good. You have a hot core, and then temperature decreases out to the surface. Okay, so whether or not this random walk occurs by scattering or absorption, independently of whatever the process is, the source function is going to be changing with radius, so that the emitted photon after an absorption event will be emitted at a local temperature. Okay, in that sense, it's different from the scattering point of view, because in the scattering case, the photon preserves its own frequencies just reflected, okay, as if it was a mirror. Okay, so it keeps the same color. But if it's absorbed and then re-emitted, it's going to be re-emitted with a local temperature, which is going to be a tiny bit different from the one where the photon came from. Okay, so we'll look at that shortly. But for now, basically, we've reached this conclusion that when we have a random walk with a constant step size, the net displacement is proportional to the square root of the number of steps if each step has got the same step size, L here, okay? However, if we look at the scattering random walk, then scattering random walk can proceed okay happily until it is completely absorbed, until the photon is eventually absorbed by the target. And the number of steps where we expect this to occur is 1 over epsilon. So epsilon is defined by equation 41, okay, and it's the ratio of the absorption coefficient divided by the total absorption coefficient, including the scattering part, okay? So we have this maximum displacement. L depends on microscopic quantities. Epsilon depends on microscopic quantities. Okay, I remind you that the absorption coefficient, okay, alpha is equal to the number density of absorbers times sigma times their cross section to the radiation. Okay, so this is right. N is number density of absorbers here. Okay, so we see that this when we take the ratio epsilon, which is n times sigma absorption nu divided by n times sigma nu absorption plus n sigma nu scattering, we see that all the n's cancel out. Okay, so we can cancel the n's. Okay, and so in the end, we see that the expected displacement depends only on the atomic processes involved in epsilon plus the mean free path. Okay, and so the mean free path we saw this one here depends on 1 over n times sigma. So it's very similar to the absorption coefficient again. That's correct, because when I multiply, okay, because when I multiply by, it's normal that it's has got the same dimensions as an absorption coefficient, so that when I multiply the absorption coefficient by a distance, I get the optical depth, which is dimensionless. Okay. So when we have an infinitely big medium, then the physical dimensions of the medium are always bigger than this net displacement, and so we say that the medium is effectively thick. Now, this nomenclature is proposed by Rybicki and Lightman. It's not very much in use. What people use is the nomenclature on the optical depth. They say that optical depth is very tiny, it's optically thin. Optical depth is very large, it's optically thick. But the concept here is interesting because it tells us that if the mean free path is small enough, then the photon will be absorbed no matter what. You know, I mean, even if you have a random walk, even if you have scattering, if the dimensions of the medium are greater than this net displacement here, given by L times square root of epsilon, then the photon will be absorbed at some point. Okay, And we call this the thermalization length because it means that if that this is the length where we expect photons to be absorbed and then re-emitted at the local conditions, which is at the local temperature and the local physical conditions. Okay. So that is one concept about the random walks. I don't know if you have any questions. Remember to just to interrupt me. Felipe, Andrés. Sí. ¿Está todo bien? Vamos, seguimos nomás.
Okay, so I have a question before going to Rosland approximation. So the thermalization length it's called that way because if the medium is larger than this length, then the medium is going to be on thermal equilibrium, let's say.
Yes. So, oops. Okay. So suppose that we have this situation. So we have we will put an example here. So this is the medium, and we have a photon emitted inside here. So there is a decay event inside the medium, and the photon escapes. Why does it escape? Because L times square root of epsilon is much larger than the dimensions of the medium. So the medium here would have dimension L. Okay.
Yes, that's because the medium is too small is smaller than the thermalization length, so the photons can escape.
Exactly. So the photon escapes eventually, and it you know, it doesn't it escapes unhindered. Okay. At most, you know, it could have maybe, so suppose that we have maybe a scattering event. So this one here could be scattered and then scattered and then whoops, it escapes. 2 or 3 scattering events before real absorption. Okay. So I mean, assuming that you have scattering. If you have no scattering, then you could escape freely without any scattering, but you could also have the same situation as described in dark blue, even with scattering, as long as the thermalization length, this quantity is larger than L. Okay. So I mean, why do we look at this and not simply L? Why don't we say, when, you know, I mean, I'm going to use the eraser here just to put colors to this argument. So we say, go back to the blue, dark blue. So we could say, so this photon is going to escape if the mean free path is much larger than L for absorption. Okay. Now, I could also say that we have the same situation as described in light blue here. If L scattering divided by square root of epsilon is much larger than L. Okay, so basically these are 2 ways of getting rid of energy. One, in the dark blue, no scattering, you have only absorption, and there's no scattering processes, and so the photon will escape if the mean free path is much larger than L. Okay, so I said we have no scattering. What does that mean in terms of epsilon? If we have no scattering, then no scattering means that this one is 0. Okay, so epsilon is simply 1. Okay, so basically this is a limiting situation of this general formula, including scattering. Okay, if we have scattering, okay, then you know you have the mean free path for scattering in each individual step before the photon is truly absorbed. Okay, but if the medium is effectively thin, in the sense that its dimension is much smaller than the thermalization length, then the photon escapes. What does that mean for the thermal, for the energy budget of the medium? It means that any spontaneous decay or any thermal emission inside the medium will be lost, right? It cannot be in thermal equilibrium, as you correctly pointed out, Felipe. It will lose its energy. It's going to cool efficiently, okay? The medium cannot thermalize, it will be, it's going to cool, right? Conversely, you could have also the opposite situation where we have a star, shining shining high energy photons like UV photons on this nebula here. And if the medium is effectively thin to the stellar radiation, then these photons are going to penetrate inside the medium and interact locally at a completely different temperature. So this would be the stellar temperature, a Planck function at the stellar temperature. And this other one here is going to be, the medium is going to have the temperature of the medium. And if it's an ionized nebula, it's going to be typically 10 to the 4 Kelvin. 10,000 Kelvin, say, okay? It depends on the medium you're looking at, but if it's a thermal plasma, then the temperature we'll see is stuck to 10,000 Kelvin. It can be a bit more, it can be a bit less, but it cannot be 30,000, less than the temperature of the star. This one can be, if it's an ionizing O star, it can be 30,000 Kelvin. Okay, so there's difference in the temperatures. Okay, they're not in equilibrium, because the photons can escape freely from the ionized nebula. So going back to Felipe's question, or comment rather, so his comment was that yes, so if the medium is much, I mean, if we are in the opposite situation where, okay, let's draw it. If we have a very thick medium, so a much bigger medium like this, okay, so this is our medium, and so we have emission here, followed by a couple of random walk processes, and then it's over, it doesn't escape, okay? So if the medium is much larger than this net displacement sigma of r, I'm not going to put it like this, then L times square root of epsilon, okay, that would be the net displacement. Then there is a chance for the medium to thermalize locally, okay? It means that we can define a temperature at this point where everything will be in thermal equilibrium at this temperature, okay? There is a chance for it. It doesn't mean that the whole medium will be in thermal equilibrium. If it was the case, temperature would be constant everywhere. And that cannot happen because we have the edges, right? I mean, we can have the border here, the edge. Okay, like if you have a photon emitted here, it will escape eventually. Okay, so the medium will always cool at the edges. Okay, and I mean, cool or heat, it depends on whether we have a star shining on it or not. But I mean, the completely stationary situation where we have no loss of energy does not exist. Look at the star here. The star inside the star, we have local thermal equilibrium to a very good accuracy because the star is much bigger than the thermalization length. So locally, you can approximate a thermal equilibrium at the local conditions, okay? And the meaning that locally you can approximate that the temperature exists and that everything follows the Boltzmann distribution and the radiation field is given by Planck's law. But of course, the star as a whole cannot be in thermal equilibrium as a whole. because it's losing energy from the surface. It's shining, okay? Yes, and there is a gradient in temperature. We have a furnace here at the center. We have a fusion producing energy in the center, and the star is losing energy at in the surface, okay? This is not an equilibrium situation. It might be approximated as a steady state situation, you know, because we have energy input and energy loss, but it certainly is not thermal equilibrium because, as you well know, in thermal equilibrium, everything is at a constant temperature. We have the same temperature in the center and in the surface. That's one of the laws of thermodynamics. When you have two bodies at different temperatures, they will reach an equilibrium with the same temperature, thermal equilibrium, okay? Well, no, in the case of a star, that doesn't work. So that star is not in thermal equilibrium. Yet, we will make the approximation that any given blob inside the star can be well represented as if it was in thermal equilibrium locally, local thermal equilibrium, okay?
Okay, so it is possible to say that there is a local thermal equilibrium, and that local, that means like the thermal length. So in each thermal length, there is one temperature, but in the second thermal length, there can be another temperature.
Exactly, Felipe.
So
exactly,
the thermal length is going to be like the scale of the temperature gradient.
Yes. So we have exactly. So we have a thermalization length here, and then we have another one here, and then another one on the other side. We have three drawn here. Okay. Here we have T of S. This is going to be T of S plus L, and this is going to be T of S minus L. If I draw a an axis on the x-axis. Okay. So this temperature difference is going to be very, very tiny, okay? Especially if we compare a thermalization length with the next one. It's going to be a very tiny difference, you know, but it might be there, okay? It might be there, and what we want to do now is estimate, you know, how big it is and how you've already seen that we are hinting at the transport of radiation flux is going to depend on this temperature gradients. Okay. So I think there's a very good discussion about the thermalization processes in the book. So have a look at it if you haven't done so already. Have a look at the section on the Planck function and the thermalization. Or why? Why is it that we have that when we have several absorption and re-emission to infinity, then we have the Planck function. Why is it that when we have several absorption and re-emission events, it means that the radiation spectrum is going to be closely approximated by the Planck function. Okay. I mean, this. Okay. If it's not clear, then you have a look at the chapter on the Planck spectrum. Okay.
Mm-hmm. So I have a little question that we had with Rafael when we had class with him, which is in Reivik-Langman in the book. The equation number 1.97. There is it's not an equal sign, it's a similar sign.
Okay, let me bring it up.
Mm-hmm. Maybe I can share a screen. No, no, you already did. So it's equation number 97.
97, okay. No. So very further away.
You are going backwards.
But did you say
It's
97?
1.97.
97. Okay, okay. You're right. Okay.
Yes.
Yes.
Yeah, so there's a similar sign there, but it says it's using 1.93 and 94a, which are both equal signs, not similar. So the question was, why is there a similar sign instead of a equal sign? Is it just a typo or is it something real here?
Okay. So let me refresh my memory. So this one is this all right, so this L star is indeed the L times square root of L. So that would be our thermalization length, I think.
Yes.
And L itself is 1 over the density times okay, I'm a bit confused because why doesn't it use density here? Okay. So this sigma is also, it's not the cross section. This is also a coefficient. It's not the cross section.
No, in that case, is the absorption coefficient of the scattering.
Okay, all right.
I think.
Okay, and if we replace L is then hold on a second. L, I think, would be 1 over alpha plus sigma nu. And the other one is square root. There is an approximation because it's not exactly the same. Look. Let me reshuffle my windows a bit.
Oh.
Okay. So let's write it down. We have L star is L divided by the square root of epsilon. L is 1 over alpha absorption plus alpha scattering in my notation. And epsilon is alpha absorption plus alpha scattering. And if we put it all in here, the star is going to be, so we have 1 over alpha A plus alpha scattering and the square root of the reciprocal of epsilon, which is going to be square root of alpha A plus alpha S divided by alpha A. Right? So
with the square root on the alpha too.
Yes. So that's going to be the square root of alpha A plus alpha S divided by the square root of alpha A. I don't get the same. No, yes, no, this is wrong. Right.
Uh,
Yes.
I think in the equation 1.93, author has approximated L nu equal to alpha nu to the power -1. I think he has neglected a sigma nu term. And if you then try to uh, fix it in equation 1.97, then that approximation will come. So if I am not wrong.
Oh, I think, Pratyush, if I follow you correctly, you're saying that this equality symbol here should actually be
So I think he has written like this 1.93 question. L nu is approximately equal to alpha nu to the power -1. Why he has written that, I am not sure, because if you do that way, then somehow I am able to get the approximation in 1.97.
But Pratyush, I think that we've done the calculation just now. We get exactly the same result, but with a strict equality. We agree on that, right?
I think what Pratyush is saying that in equation 90, the mean free path is, well, the mean free path is 1 over the optical depth.
Which
Yes.
equation, Felipe?
So in 93, we have
Yes.
the mean free path is 1 over something.
Yes.
Yeah,
Now, this something is the optical
over
depth. And that in equation 90, there is an approximation there of the optical
In
depth.
equation 90 or
90.
190.
Yes, there. So if we have a optic analysis of the optical depth, if we use that optical depth of with the exponents 1, then we get the mean free path in 93. So there is an approximation there.
Oh, I see. Yes.
93.
So basically, I think we all agree. I think what should be written here is this. Is an approximation here, right?
Yes, I
The
think
same thing. I mean, I've got problems writing down with this PDF here. So, so I think what you mean is replacing this equality sign by an approximation.
Yes, I think that's what Pratyush said, right?
I think I agree with you. Okay, I think that this expression here, it would be, well, it can be looked at as a definition for the mean free path, but you can always say, I define this mean free path such, but when you say, no, this is going to be the exact displacement of the photon before it is absorbed, that's a different story, right? I mean, we are I mean, this is an approximation. I mean, it's not, you can define L, but if you use it later on to estimate the actual length over which a photon will be absorbed, then this is an approximation, right? I think that's the main difference. I wouldn't worry too much about it, Felipe. Seems,
yeah, it's something Rafael told us to ask you.
Okay, yes. No, I mean, it seems okay. I mean, I don't like much this, why is there an approximation sign here and not there? Yeah.
Yeah, well, if it's not to worry, if you say it's not to worry,
No, I think it's okay.
I think it's okay there.
Yeah,
Thank
yeah.
you. Thank you very much.
But while we're looking at the Rybicki alignment book, I just wanted to, I mean, we're nearing the end of the class at the moment. So remember to look the thermal radiation here. Where was it? That's it, yeah. Yeah, so these arguments. So this argument is what, yeah, have a look at this. At the first chapter of the thermal radiation, and why the specific intensity spectrum is a universal function of the local temperature. Okay, convince yourselves of that. Okay, ciao. See you on Thursday. And I hope you recover soon, Pratyush, and that everything is fine for your family.
Thank you. I hope so.
Ciao.
Ciao.
Goodbye.
Ciao.
Take care, Pratush.
Yeah, thank you.